Welcome to the Explainer. You know, in every single high-speed electronic device you own, from your phone to a satellite in orbit, there's a hidden speed limit. And no, it's not a software bug, it's a fundamental law of physics. It's called the Miller Effect, and today we're going to dig into why it exists and, even better, how engineers totally outsmart it. So here's our game plan. First, we'll figure out why even a perfectly good amplifier can suddenly fail. Then we'll meet the culprit, the Miller Effect itself. After that, we'll learn the language engineers use to fight back, see it in action in a super common circuit, and finally, we'll reveal the elegant solution that really tames this beast for good.
All right, so what is the actual problem we're trying to solve here? Let's kick things off with the one challenge that every single high-speed circuit designer has to face. This is the big mystery, right? You can have an amplifier that works beautifully for, say, audio signals, but then you try to push the speed up into the megahertz or gigahertz range, for things like Wi-Fi or 5G, and its performance just completely falls off a cliff. So what's going on? Well, the reason for this epic slowdown isn't obvious at all. It's actually a really subtle effect, and it's lurking inside the very components themselves. So let's meet our culprit. You see, in the real world, no component is perfect. Every single transistor has these teeny tiny, almost invisible capacitances that are just part of its physical structure. The one that causes all the trouble for us is called CGD, and it's the capacitance that sneakily connects the input of the transistor to its output. Okay, so decades ago, a brilliant engineer named John Milton Miller figured out a way to analyze this whole mess. His theorem lets us take that tricky floating capacitor and mathematically replace it with two much simpler ones. Now, this isn't just a math trick. It's a way to reveal exactly how this tiny component messes with the circuit's performance. So the process is pretty straightforward. You find that floating capacitor, and then Miller's theorem does its magic. But here's the crucial part. The part that's both the magic and the problem is what happens to that new capacitor that suddenly shows up at the amplifier's input. And boom, this right here is the heart of the Miller effect. That tiny parasitic capacitor, CGD, doesn't just get moved to the input. No, it gets multiplied by 1 plus the gain of the amplifier. And since amplifier gains can be huge, like 50, 100, or more, this turns a completely insignificant capacitance into a massive one. But why? Why does this happen? The intuition here is everything. Because the amplifier's output is swinging with a much, much larger voltage than the input, that tiny capacitor starts demanding a huge amount of charge just to keep up. So from the input's point of view, it feels like it's trying to charge an absolutely enormous capacitor. And that is what slows everything down. Okay, so how do engineers actually measure and predict this effect? Let's take a look at the special language they use to map out a circuit's behavior at high speeds.
It really comes down to two key ideas: poles and zeros. Just think of a pole as a speed bump for the signal. As the frequency gets higher, the pole slows the signal way down. A zero is kind of the opposite. It's like a shortcut that can sometimes speed things up. And that giant Miller capacitance we just created, well, that's like putting a massive speed bump right at the front door of our circuit.
Now, to see all this visually, engineers use something called a Bode plot. It's basically the essential treasure map of a circuit's performance across all frequencies. It lets us see exactly where these poles and zeros, these speed bumps and shortcuts are, and how they're going to totally change our signal.
And here's a really important insight. Pretty much any point in a circuit that has some resistance and capacitance is going to create a potential pole. This means that as circuits get more complex, we're basically navigating a minefield of these little speed bumps. But the Miller effect, it creates the biggest, baddest one of them all.
Okay, theory is great and all, but let's apply this to one of the most fundamental building blocks in all of analog circuit design and see what really happens.
So here it is, the Miller effect out in the wild. In this very standard common source amplifier, that tiny, innocent-looking CGD gets multiplied by the amp's high gain. The result? A huge, speed-killing capacitor right at the input, which is pretty much the worst place it could possibly be.
And the consequence of this is, well, it's bad. This massive new input capacitance creates what engineers call a dominant pole, a speed bump so large that it becomes the main bottleneck for the entire amplifier. It basically single-handedly sets the speed limit for the whole circuit. Now, what's interesting is at super high frequencies, the signal can actually leak directly through that tiny capacitor, causing other weird effects. But for us, that dominant pole is problem number one. Okay, so if the Miller effect is the villain holding our speed hostage, it's time to meet the hero of our story. A really clever circuit design built specifically to defeat it. The cascode architecture is just a brilliant piece of engineering. What it does is add a second transistor that acts like a shield. Now, the first transistor's output connects to a very low impedance point, which means its own individual gain is tiny. By basically isolating the input from the final high-gain output, we break the whole feedback loop. The Miller multiplication never even gets a chance to start. The source material just nails it with this quote. The cascode gives us the absolute best of both worlds. We get the great input characteristics we wanted from our original design, but now we also get the high-speed performance of a circuit that isn't being dragged down by the Miller effect. It's just an elegant solution. And here it is, the beautiful result. Instead of multiplying that parasitic capacitor by a gain of, say, 50 or 100, we're now multiplying it by a gain of just 2. The speed limit has been effectively removed. The Miller effect has been neutralized. All right, let's pull it all together and see what this really means for all the technology that we use every day. So what's the bottom line here? The Miller effect is this unavoidable speed bump that's baked right into the physics of transistors. We use the language of poles to understand it, and then we use clever designs like the cascode to defeat it. High-speed design isn't about magic. It's the art of intelligently managing all these hidden forces. And of course, the Miller effect isn't the only challenge out there. Other circuit designs solve this particular problem, but can introduce their own weird quirks, like a strange kind of instability that engineers call negative resistance. And this leaves us with a final, kind of mind-bending thought. We spend all this time and energy fighting these unwanted effects and instabilities. But what if we could just flip the script? That unstable, negative resistance we just mentioned, it's actually the core principle used to build oscillators, the very things that act as the heartbeats of our digital world. So it turns out, in circuit design, sometimes your biggest problem can become your most powerful solution.